lecture, we had successfully managed to sort of set up this problem, the analysis of Thomas Precession. We studied a boost from the lab to the rest frame of the electron, which I had depicted as orbiting a hydrogen atom. However, to be clear, the motion that we're analyzing really is valid for any arbitrary motion in the xy plane. Ultimately, we're going to talk about the hydrogen atom, and for simplicity, I kind of set it up as a circle. But the subsequent boost from this electron's rest frame to its next rest frame, or its rest frame a moment later, is given by some arbitrary infinitesimal boost in the xy plane. There's nothing about this little infinitesimal boost that's going to force it to stay in a circle. So our analysis is quite general, although it's easy and nice to picture this kind of motion. And we calculated this boost, the matrix that will give us the transformation from lab coordinates to the electron's rest frame coordinates. And we also calculated the matrix that will give you the lab coordinates to the boosted electron. I'll call this the boosted electron, or S prime frame. And those two matrices were given by these guys. The first one was simple, right? The first one was just a straightforward application of our well-known pure boost in an arbitrary direction matrix. So it's a nice clean matrix transformation. Yeah, and in the particular case we were considering, it just reduced to this very simple matrix with just this one portion. Now notice, this is from the lab to the electron frame. When we apply it, we actually want it from the electron frame back to the lab. So we're going to change the sign of these two things when we actually apply it in a moment. The other one was much trickier, and we spent more of our time on it. We still used the basic matrix, but we simplified it and made first-order approximations, and we were ultimately able to get a matrix from the lab to the boosted electron, the S prime frame, and it looked like this. And we studied this very carefully, compared it against Jackson, who uses the same matrix, and this turns out to be right. It's kind of strange, you've got these gamma cubes, and what's really important to remember is gamma here refers to 1 over the square root of 1 minus the finite boost beta x squared, right? That's what gamma is in all of these cases. So gamma doesn't take into account any of the little infinitesimal boosts. And ultimately, that is why we go to first order with everything. But we got it. We got there. Wasn't easy. Went through a lot of analysis. But now we are ready to do the transformation that we're after, right? We're after the transformation from the electron's frame to its little mini boosted frame, its infinitesimally boosted frame. And the way we're going to do that is we're going to take the electron, push it back to the lab by using the inverse of the lab to the electron frame. So we need the inverse of this matrix. And then we follow it with the matrix from the lab to the boosted electron frame. And we've calculated both of these in the last lecture. But as I said, in order to get this inverse, we have to change the sign. So you see that the two minus signs are now missing. And we can execute this matrix multiplication in the standard way. Multiply each element of a row on the one on the left by a column on the one on the right, add everything together. And when you do it, you end up with what we're going to call the Thomas matrix. I think Jackson calls it AT. So we'll just call it lambda sub Thomas. Now, just for completeness' sake, I actually did each of the calculations here. If you want to pause and look, you can see the lambda Thomas 0, 0. Here's what the sum looks like. I did it for each of the terms. Wasn't totally obvious, actually, but we definitely did verify it. Let's see, this one I want to... Holy crap, this one's bigger, huh? So this, I guess, A21 was the hardest one. But regardless, we end up with this matrix. And this matrix here has a very interesting but kind of obvious property, something you would have expected. First of all, we take note that it is not symmetric, right? So this cannot represent a pure boost. But here's the thing. Every term that's not 0 or 1... Oops, holy crap. This 0 down here is obviously not supposed to be a 0. It's supposed to be a 1. But everything here that's not a 0 or a 1, first of all the 1s are on the diagonal, right? So that's one thing to take note of. The other thing is that all the off-diagonal matrix elements that aren't 0 are infinitesimal in size, right? This sloppy writing here, but that's a delta. All of these are this is delta by and delta bx, delta bx, delta bx, delta bx, delta by. They're all infinitesimal. This matrix here has off-diagonal elements that are only infinitesimal in size. And by now, you should get the feeling that transformation matrices that are structured like that, with 1 down the diagonal and infinitesimal elements off the side, represent infinitesimal transformations. And that makes perfect sense, right? If these infinitesimals were driven to 0, you would just have a 1 on the diagonal only, so that you would have the identity matrix, which means no transformation whatsoever. So we're looking at an infinitesimal Lorentz transformation that is not a pure boost. And in some sense, that's to be expected, right? Because the finite boost was from the lab to the electron, and then from the lab to the electron's infinitesimally later position. The bulk of that is a boost in the finite amount beta x. The rest of it that's left over is delta beta, vector delta beta. So you're boosting beta x here, but you're kind of, you're unboosting a beta x here because you're going from the electron to the lab, and then you're boosting back a beta x here. It kind of cancels out. The bulk of it cancels out, and all that's left is just a sampling of the infinitesimal boost from S to S prime, which is what you're after, right? We're after a boost from S to S prime. So now we have this infinitesimal matrix, and that's going to make our work actually a lot easier. So now we're going to go back and we're going to take a look at the idea of how our transformations, like the Lorentz transformation, which is the example we'll use, how are they understood in infinitesimal terms, and how do we build up a finite transformation matrix from an infinitesimal one? And how do we use that to generate or to create or identify, I guess I should say, the generators of the Lorentz group of transformations, right? An arbitrary Lorentz transformation can be made up can be built up of a finite set of generators that are appropriately handled. And we need to identify those generators, and then we're going to convert this into the form based on the generators of the Lorentz group. And then from that, we're going to tease apart what is the rotation and what is the boost. Normally, this would be really hard. If you were just looking at an arbitrary Lorentz transformation, it'd be difficult to figure out what the rotation is and what the boost is, and to separate it into those two pieces. A lot of work has been done on it, and it is a solved problem, but it's really, really hard. But the fact that it's infinitesimal is going to make it easy. So let's have a look at how we're going to exploit that. So here are the two equations that we really need to have a look at. You need to be very familiar with these two things to proceed on in QED and quantum field theory, even general relativity to some extent. This is just so de rigueur. It shows up everywhere, and it's just critical to all modern theories of physics, at the elementary level at least, that it's something we need to see. And one of the reasons I've chosen the problem that we have here is it gives us a chance to do these diversions into these critical areas. And we've already looked at this a few times in the quantum mechanics course. I think we did it once or twice for the momentum operator and some other things, but in this case, it's slightly different. I mean, our requirements are different, but the process is the same. What we're saying is that an infinitesimal transformation that matters in physics, almost always, with very few exceptions. There are exceptions, but the ones that they're treated uniquely, so you don't have to worry about them now. But an infinitesimal transformation can always be written as the identity operator and a small infinitesimal parameter times some matrix, right? And this represents the infinitesimal transformation, and the art is to figure out what kind of matrix here provides an infinitesimal transformation for whatever transformation you're studying. And in our case, we're studying the Lorentz group, but you could be studying, say, just the pure rotation group, or you could be studying the group SO3 if you were studying, say, quantum chromodynamics, or not SO3, SU3. So getting at what M is really important, because then you can figure out the infinitesimal transformation. And why you want to do that is once you understand the infinitesimal transformation, you realize that a finite transformation is just the application of an infinitesimal one many times. So you take a finite parameter, the same matrix, and you divide the finite parameter by n, and you execute this matrix multiplication n times, and you're basically repeating the same small transformation over and over again, and you build it up until you end up with a finite one. And this, of course, is this limit as n goes into infinity is always written as e to the theta m. And this is important. You have a plus sign here, you end up with theta m here. What's in the numerator here ends up with theta m here. And now Jackson, then instead of writing e to the theta m, he just starts with e to the l. Whatever this is because this is another matrix. That's a parameter and that's a matrix. So he goes with e to the l. Now, what's usually going on, of course, is that there's more than one m, right? So this is not a general expression for all possible infinitesimal transformations. What you normally have is you have a collection of a finite number of m's, and each one of those gets its own parameter. So the way this is often written, or usually written, is E, the parameter list is a vector, and M is a vector of matrices, right? And so this ends up being, epsilon 1 times M1 plus epsilon 2 times M2, and the sum of those ends up making this guy, right? So we always see this. Happens over and over and over again, and it's something we have to be very used to. Now, one way to approach this is to say, okay, I understand how to make an infinitesimal transformation of the kind I'm interested in, and literally build this. You start with the identity, and you figure out by hook or by crook what M is. And it's a bit of an art form, but once you figure out what M is, then you just calculate this directly, right, using the fact that this is defined by the Taylor series. So the calculation of this looks weird. You're raising e to a power, but you interpret that as this Taylor series where the matrix shows up here, the matrix is square up here, the matrices cube up here. And calculating this is a bit of an art too, because obviously you're not going to do an infinite series, but what you end up seeing typically is a pattern emerge that allows you to combine terms, infer things from other Taylor series. We did a good example of this in the Lie group section of the course. The point is that this is something you have to become familiar with, how to take the exponential of a matrix, and understanding this concept very, very well. Now, it doesn't help that there's a lot of different conventions out there, and I'm going to try to zero in on two separate conventions to do this. But this art of figuring out what M is, figuring out what this infinitesimal matrix is, and multiplying this up, that art, we're in a good position right now because we actually know. We know what the finite matrices are. So we can actually go the other way. We can use the finite matrices to calculate the infinitesimal ones, right? So that's lucky. That's usually that. Well, I don't know if it's usually one way or the other, but in this case, we know the finite matrices. We need to calculate the infinitesimal ones. So how would we do that? Well, the technique is pretty simple. We understand that our finite transformation matrix can be Taylor expanded just like anything else, where we start with the identity operator, and then we take the derivative of the finite matrix with respect to the variable that's changing. In this case, I've identified it as theta. Calculate that derivative at theta equals 0, multiply by theta. Do the same thing with the square, or the second derivative of lambda, and multiply by theta squared. Again, calculating that second derivative at theta equals 0. And this is the Maclaurin series for the finite matrix. The idea, though, is that we're only interested in the infinitesimal part of things. So we get rid of everything that involves the square or higher of our parameter, make our parameter infinitesimal, and then just calculate this derivative and evaluate it at theta equals 0. So to exercise this for our particular problem, let's look at our boost, right? This is our basic boost from the lab to the electrons, or the S frame. And we have gamma and beta gamma. The parameter that drives this boost is beta, the velocity beta. This is just a generic boost in the x direction with a velocity of beta. So we know gamma is a function of beta, but beta is the parameter for this boost. So we're going to take the derivative of this matrix with respect to beta. And that means element by element. We're going to take the derivative of gamma with respect to beta, the derivative of minus beta gamma with respect to beta, and put those and replace these elements with those. And so to do this, the derivative of gamma with respect to beta is given by this, and the derivative of gamma with respect to beta evaluated at beta equals 0 is 0, right? Because this whole product is multiplied by beta. So that was easy. So this first element here becomes a 0, right? And then we do the same thing. We take the derivative of gamma beta with respect to beta, which I've done here. And this part goes away because beta is evaluated at 0. And this part calculates to -1. So then we replace this with -1. And this ends up being the matrix that slides into the position right here times this infinitesimal amount, which is exactly the form we're interested in. So we have now discovered M. Right? We've discovered M. We take the matrix we calculated and multiply it by our infinitesimal movement, and that is going to be our generator. It's called a generator. It's going to generate Lorentz boosts in the x direction. So this is our generator that generates Lorentz boosts in the x direction. Phew. By the way, had we used the different formalism, remember here we used the gamma beta formalism, we could have used the rapidity formalism, in which case the boost would have looked like this. A finite boost would have looked like this hyperbolic cosine, hyperbolic sine. Remember, this is the connection between the two formalisms right here. The velocity beta is given by the hyperbolic tangent of the rapidity. Gamma is the hyperbolic cosine of the rapidity, and beta gamma is the hyperbolic sine of the rapidity. And this is what saves you, because taking the derivative of this was, certainly wasn't hard, but it was a mess. But taking the derivative of the hyperbolic sine is actually trivial. Although, interestingly enough, the derivative of the hyperbolic cosine is not minus the hyperbolic sine. It's just the hyperbolic sine. I forgot that. It confused me for a while. It's like, why are my sines working out? But the derivative of cosine is minus sine, but the derivative of hyperbolic cosine is just hyperbolic sine. Anyway, you take those derivatives and you end up with this, and then you evaluate it at theta equals 0, and you end up with this, which is the same thing that we ended up with here, right? So this formalism actually is a little bit easier to do this kind of thing in. Just remember this formalism exists, because in a lot of textbooks, you will see them operate in the rapidity formalism, which is, I don't like it as much, only because I got to admit, I'm just so used to this, right? I love these gammas, and actually this notion of gamma and beta shows up again when you study the Dirac equation a bunch. Although there is potential confusion, right? The gamma matrices of the Dirac equation are not the same as this. I don't know. These are almost entirely equivalent. Once you make this connection, it's pretty much pretty easy. Anyway, so we've discovered the generator of a boost. That was pretty good. Now, what about the generator of a rotation, right? Well, we know what a rotation looks like. Again, we know the finite form of a rotation. Here's a rotation about the x-axis. We take those derivatives of each term, we evaluate at x equals 0, and we end up with this generator of a rotation. So we can do this for each of the things. We can do it for each of the 3 rotations and each of the 3 boosts, and we can get 6 generators out of this. Now, and Jackson basically does not actually do this, literally. Jackson presents the generators. And the problem, of course, is the convention. So let's have a look at these conventions so we can understand how to sort of anchor our thinking. And I believe this is the place to anchor yourself. The definition of the exponential is this limit. That is e to the x. And then the first thing you realize is that if you could break up x into our matrix times some finite number over n, where this becomes a constant, and this plays the role of x, right? So that's always the way this stuff works. And what happens is the various conventions just fool around with this sign and some of the notation about how to handle the x over n part. So, for example, if you go to Wikipedia's actually got one of the weirdest ones because it seems to be different for the pure boosts and the pure rotations. But as an example, their pure boost is defined with a minus sign here, which ends up being a minus sign in the exponential. And they're defining just a pure boost in the x direction, so they're dealing with the generator of the boost in the x direction. But otherwise, that's really not much of a thing. It's literally, conventions aren't meant to be super complicated. They're just confusing when you go between different books, and you will. You will inevitably choose to use different books when you study QED. If no one book is all that good. Well, there's a lot of good books, but you will use multiple books. So, but in Wikipedia, you end up with this boost with a defined minus sign, but the rotations don't have a defined minus sign. So when the rotation form, they must have had a plus sign up here, right? And then this would have been theta over n, and this k would have been a j. And notice that they're using this dot product notation, right? So, of course, what's going on there is you have the boosts in the, let's say boosts in the x direction, boost in the y direction, boost in the z direction, rotation in the x direction, rotation in the y direction, rotation in the z direction, right? So that you combine these, and then you're going to have a finite translation or finite boost amount in the x direction, a finite boost amount in the y direction, a finite boost amount in the z direction, and you put these guys together as a vector, these guys together as a vector, and you just write it like this, right? An alternative form would be use Einstein summation notation, right? Like that, which I think somebody does later on. But here's another convention. This convention, everything is positive, right? You have, first of all, they combine the boosts and the rotations into one exponential, which you're allowed to do because everything, and they use the dot product notation, just like I mentioned a moment ago. And notice that there's no negative signs. So even if they didn't explicitly cite their infinitesimal form, like was done up here, even if they didn't explicitly cite their infinitesimal form, you can figure it out that it's going to be with the plus sign. Then here's a guy who actually reorganized the vector. So xy is at the bottom and z is first of the spatial terms. And so this changes the structure of things. But notice that in their exponential, you end up with this factor of I. Right? So some guys will do that. Some guys will take out a factor of I. And basically their infinitesimal form, his infinitesimal form, you've got the minus sign from that minus sign. But now he's going to pull out an I phi over n j3 to the n. That's this guy's infinitesimal form. And this factor of I came out. And what that has the effect of doing is it turns J3 into a Hermitian matrix, right? J3 would normally have been just an anti-symmetric matrix, right? J3 in this case is just anti-symmetric. Here it will be full-on Hermitian. And that's useful in quantum mechanics, not necessarily particularly useful in pure electrodynamics and special relativity, but it is useful in quantum mechanics. And it's sort of normal too. It's become sort of the habit of people to use to pull out that I. So when you do that, of course, the I comes out from these matrices, and you end up having these matrices have complex values now. Also, notice the fact that z is first shifts everything around so that now the rotation in the z direction, the values are in the lower right instead of here where we found them. Actually, I think I said this incorrectly before when we did our analysis of this rotation. I think I said this was around the x. I think I said x, but I meant z, right? This matrix here is a rotation around the z-axis. And you can tell because it's going to screw around with the x and y components but leave the z components untouched, right? So I think I said when I did this, I think I said x, but I meant z. And so but this guy, the rotation around z, this J3 actually puts the i's in a different place because he's reordered x, y, and z for some reason. So I didn't expect to see that convention. Here's another convention where this is the way I like to see it, right? He lists everything out. He lists out his infinitesimal form. Notice he has the minus sign and the I, the infinitesimal parameter, and the generator. And there's the identity matrix. So that's really good. For his rotations and his boosts, same way. He pulls out the I for the boosts too. What's interesting is because if you pull out the I for the boost, K still does not become Hermitian, right? Remember, I'll show you in a moment, but, well, let's see. Here, look at K. If you pull out I from K, you leave two I's behind. And if you take the transpose conjugate, that's not the same. So K is not Hermitian, but of course, boosts are also not eigenstates of quantum mechanical states either. We don't label states by their boost state. We label them by their angular momentum, and it turns out this guy is actually Hermitian, right? This is a Hermitian. You take the transpose conjugate, you get the same thing. So these guys are Hermitian. But anyway, they still pull the I out, despite the fact that I think once you pull the I out, you might as well pull it out of everything, I guess. But notice this is for a pure boost, this is for a pure rotation. The general Lorentz transformation, they kind of merge these J's and K's into a two-component object. We're not going to talk about that, but you will often see this, and if you do, you're going to have to figure out, you're going to have to study what this two-component object is. We'll probably get to it much later in our introduction. Anyway, but ultimately, Jackson. Jackson is sort of the model we're following. What does Jackson do? Well, Jackson chooses these matrices for the generators. And he just states that these are the common generators that are used. Notice he does not pull out an I, obviously. And but notice that the signs, you may remember, we got minus ones here. We would have had minus ones had we done these boosts. And he uses just positive ones. And likewise, his rotation matrices are flipped in sign from ours. So this implies that he's dragged these matrices out using this minus convention, right? I minus epsilon m, which is fine. I mean, that's the convention that he's ultimately tried to use, and that's the convention he went with. So with this convention, using this Jackson convention for the generators, what do we get? We get the identity matrix minus 0 times a rotation around x, 0 times a rotation around y, and this finite quantity here, or this infinitesimal quantity, sorry, that's the opposite of finite, it's infinitesimal quantity, rotation around z, and then a little bit, this infinitesimal boost in the x, and this little infinitesimal boost in the y. I have a 2 there. I'm mixing the notations up, but this should be a y. And then there's no boost in the z. So this is how we make the infinitesimal matrix using the Jackson convention. So the Jackson convention is this, by the way. It's the minus signs are in play. There's no i's, and ultimately the finite boost is e to the minus omega dot j minus zeta dot k. So this is the convention that Jackson uses. Now I want to also show a convention used by Schwitzenberg. He wrote a textbook that was recommended to me by the Patreons, or somebody on when I was streaming one day recommended this book, and I got it, and I kind of enjoy it. It's a good book. It's called Physics from Symmetry. And I like it because he kind of handles this convention question. Well, I don't think he addresses it specifically, but he definitely makes it very clear what he's doing. And in his convention, right, his convention uses the plus sign and the I. So I thought I would show this one too, because it's literally the opposite of Jackson, which uses minus sign and no I, right? So if you use Schwitzenberg's convention, you end up with these I's everywhere, but they're immediately compensated for by these matrices. And you add this up, you end up with exactly the same matrix, the same infinitesimal matrix as you would with Jackson. It's all a matter of convention. And that's a big trick with studying QED. It's almost a prerequisite, is to understand that you're going to have to dig into different conventions. Just get used to it. Don't complain about it. And certainly don't argue which is better, right? In Schwitzenberg, right, sure, if you're studying special relativity, you don't need to do this, but you're not. You're going to study QED. You're going to study quantum mechanics. Then all of a sudden, this I becomes something you do need to want to think about, because you are interested in what's unitary, what isn't, what's Hermitian, what isn't. If you're doing pure electrodynamics like you are in Jackson, none of that matters, right? All you need is the infinitesimal form of the matrix. So anyway, the point is we've now broken this down into its constituent parts, the infinitesimal matrix into its constituent parts. But that's all we want, because our actual thing of interest is in fact an infinitesimal matrix. This guy right here, right? And we now can write this guy right here, we just did, as the sum of generators. So now it's time to take the work we did and tease apart the rotation from the boosting. And to do that, I guess we'll go to this page here, and we will we'll zero in on this format, right? We're following Jackson literally, so we will zero in on this format. And what we're going to do is we're going to write this in a condensed form that separates these guys from these guys in a nice and articulable way. And that is this expression right here. Let me box it up. This expression right here is basically rewriting this in a single statement that uses this dot product formalism. And this part right here captures the directionality of this rotation. Beta is a vector, right? And it is the initial boost vector. And we divide it by its magnitude, so we're turning this into a unit vector. So it's a unit vector of that big initial boost from the lab. And then this delta beta is a vector that represents some vector, some infinitesimal vector in the xy plane. So this is x, and this is in the xy plane. So this cross product is always going to be x hat cross y hat, essentially. I mean, that's the direction it's going to be in, which, of course, x into y is going to be z hat, which is exactly what the rotation is. This rotation, if we look up here, only exists in Z. This is SZ, right? And all the others are 0. So this captures the direction, and this dot product captures this piece of the infinitesimal sum. Remember, the matrix we're dealing with is an infinitesimal transformation. And then, of course, this coefficient here is just this coefficient here. So this beta will go into here now, actually. So if I wanted to clean this up a bit, I could take this out, and I write this as beta, the vector, and then I square that, right? And then as far as the boost goes, there are two legit boost components. There's this delta bx and delta by. Delta bx is parallel to the initial large boost, and delta by is perpendicular to the initial large boost. And we're going to label them that way. So we'll have gamma squared delta bx, which we're going to call delta b parallel, and then just gamma delta by, which we'll call delta perpendicular. So this is in the x direction, this is in the y direction. When you dot it with k, you'll get this piece with kx and this piece with ky, and that's what you get right here. Right? So this expression here captures all of this in a tidy little form. And it is the matrix that we're interested in. It is infinitesimal. Now we have separated the rotation part from the boost part. And you couldn't have done this if it wasn't infinitesimal, because if it's not infinitesimal, you can't do this decomposition. But it is, and now we're well on our way. In fact, the Thomas Precession expression is this guy right here, it turns out. There's a little bit more thinking to do, but that's ultimately the magnitude of this infinitesimal piece. This delta B, this is a change in the velocity. This is the velocity. This is a change in the velocity. So if I take this term here, if I take this term and I divide it by a small increment of time, this change in velocity becomes an acceleration. So I have a velocity cross an acceleration, right? Usually you switch them, so you have an acceleration cross a velocity, and then you change the sign, and then you end up with that gamma minus 1 over beta squared. The gamma minus 1 over beta squared, here's the math, keeping in mind that beta squared is 1 minus 1 over gamma squared. You just run a little bit of algebra, and you get gamma squared minus 1 over beta squared, which is what this term is. And you just do the calculation a little bit, and you end up with gamma squared over gamma plus 1, which means that this now becomes our final expression for this little Thomas matrix, which takes us from the electron's rest frame to its slightly boosted frame a moment later. And I think I'll leave it there, because this part breaks. This is really where the magic happens, right? And the idea is that if you want to figure out just the rotation part, what you can do is you realize that this object, even though it's I minus this piece, it actually breaks down, because it's infinitesimal, it breaks down into a pure rotation part and a pure boost part multiplied together. As long as it's an infinitesimal rotation, this guy is actually the same as taking just a pure little rotation and just a pure little boost. Because if you multiply these two together, you'll discover that you end up with this expression here plus some second order terms that go away, because we're dealing with infinitesimals. This infinitesimal thing is really important. And so this doesn't look like it would be it doesn't look necessarily like it's this and this, but once you realize you throw away second order terms, you get this times this. Likewise, I wrote this as T boost times T rotation. I could have commuted these. Matrices don't normally commute, but if I commuted these and I did this calculation, the parts that are unequal are again second order. So it doesn't matter what order you do this in as long as it's infinitesimal. And that's really important. That's true for rotations too. It's famously true for infinitesimal matrices. But this infinitesimal nature of things just happens so much in this work. It just got to be really, really used to it and really facile with it. But the point is now we got our rotation matrix, right? This is the little mini rotation that happens when you do this boosting. The important point being that this here is the angle of rotation. I forgot some vector signs here. Those are vectors. Right? These are vectors. Because otherwise this dot product doesn't make sense, right? But now the amount of rotation is this thing right here. And it remains only to interpret how this change in rotation fits into our overall analysis. So this actually may be the hardest part. We've done all the math, and the answer that we got for the Thomas Precession, you could practically stop now, right? You could say, okay, well, we found this famous formula for the Thomas Precession. Well, it's actually beta cross delta beta, and you have to, this is delta r, and then you have to take it over delta t, and when you get delta beta over delta t, this becomes the acceleration, right? And so what do you end up with? You end up with gamma squared over gamma plus 1 times c, and then this becomes v cross a, right? And where a is the acceleration, right? These are two vectors. So that's sort of this, that's the answer for Thomas Precession. So if you wanted to stop now, you probably could. It's worth it to try to get your head around exactly how these coordinate systems work. And I'm telling you, this isn't easy, but the way it kind of goes is like this. We have this electron here. We've figured out how to calculate going back to the lab and then boosting back to the lab and then boosting here. And what we discovered is that introduces this delta R. But we want to understand the electron in terms of these direct boosts, right? If you were just sitting here in the electron's frame, you don't see, you just have a little delta B, right? You've got a delta boost going on, right? And it's a pure boost, right? So there's no rotation. So you're kind of interested in this reference frame, which we would call S, I guess, double prime, the way we're doing it now, where S double prime is a Lorentz transformation directly from S, directly from the electron's frame, using just the pure boost into S double prime. And that's going to end up being different from S prime because, as we've seen, S prime, the way we've calculated it, included this rotation. So in order to understand, and S double prime is actually kind of what we're thinking of, because we're thinking of this electron boosting infinitesimally over and over and over again, and each successive instance that happens is just a pure boost. And so we're tracking frame by frame by frame of the electron. So the only way to keep track, and we want to do that because the reason we want to do that is we want this frame to be inertial. If it's rotating, it becomes a non-inertial frame. If all it's doing is infinitesimally changing its velocity, it actually stays inertial. But as soon as you add rotation, it doesn't. So we're interested in that inertial frame. And the reason we're interested in the inertial frame is because all the laws of motion apply in the inertial frame. In particular, one of the laws we're interested in is this precession, right? If you have a vector A that's, say, precessing in a reference frame, in this case the reference frame of the electron, and A would be the spin of the electron, if it's precessing, that's fine. The precession in the lab is the precession in the rest frame, but if the rest frame has its own motion, you have to add this piece to it, right? So we have to know what this is in order to get the precession in the lab. So looking at this boosting process from the perspective of the lab gives us some kind of new extra rotation, this Thomas rotation, but looking at it from the electron does not. the important point is all the electron sees when this goes down is this. It only sees this little boost. It doesn't. This rotation is what the lab is seeing. This little boost here is the only thing. This is the direct boost, right? This isn't going back to the lab and then to the new electron position. This is the direct boost from the old electron position to the new one, and it's a pure boost. So so that's a different frame, right? That's now a different frame of reference. This S double prime is just this direct boost as opposed to going back to the lab and to this electron. So how does the lab get into this reference frame? Well, the lab just has to execute a rotation by minus r in its sequence of Lorentz transformations. That is, the lab has to execute this boost to get into S prime, and then on top of that, after it's executed this boost, it has to execute Lorentz transformation of minus delta r, right? Minus delta r. And then it will be in this purely boosted, infinitesimally stepwise electron rest frame. And that's where our formula comes in, right? We now have the precession rate, right? This Thomas precession rate is going to be the amount that you have to unrotate, which is this r, over delta t, where this delta t is the lab time, right? This is the time in the lab. And that is going to be equal to, well, we just did it on the other page, gamma squared over gamma plus 1. Let's see, it's A times V, but you have to go over C squared, right? Because you have the delta beta is delta V over C, and then V is, beta is of course V over C. So you end up with this expression. Let me see, is there a minus sign here? No, I switched these two around, so that gets rid of the minus sign, right? Remember the A and the V and the V and the A. So this becomes the expression for the Thomas precession. This is what the lab would observe in order to keep that electron frame inertial. And this is why this is the amount the electron frame is not inertial, right? So this is the compensating factor. And you'll notice that the sign comes in as a negative, right? So it's sort of going in the opposite way that it would be rotating, right? And so that is the answer for the Thomas precession. Now, sometimes you see this with a gamma cubed here. If you see it with a gamma cubed, what's usually going on is that this T is actually not the lab frame, but it's the rest frame of the electron, right? And the rest frame of the electron is off by a factor of gamma. It's the normal time dilation. And this is the final expression for the Thomas precession in Jackson. Phew, quite a mess, but it was great. This was really good because we really got a chance to understand infinitesimal matrices, right? This was really, really important. That is, reviewing this breakdown was critical. Getting exercising our relativistic matrices, looking at all of these different conventions. This is all good prerequisite stuff, right? This is stuff that you should be able to handle and do. We kind of dug into the Jackson. We did a lot of work with. We did a lot of really good work with first order approximations, which is something we do all the time. You got to get really comfortable with doing that. Never be afraid of it. It was pretty hard, I'm not going to lie. It was a bit of a pain, but we followed and tracked all of this stuff. Here it is in Jackson, the expression that we ended up with. And here it is in Jackson where he tries to kind of interpret all of this stuff to get you to the actual Thomas precession. What we didn't do is we didn't really exploit the fact that this guy was moving in a circle, right? Remember, delta beta was an arbitrary little infinitesimal boost. The idea is that when we study the hydrogen atom, which is a critical prerequisite topic. We will, in fact, talk about the orbital angular momentum and how this Thomas Precession affects our understanding of spin precession and the splitting of atomic orbitals and things like that from the non-relativistic perspective, which is ironic, right? Because Thomas Precession is a relativistic effect, right? And you can tell it's a relativistic effect if you go to this expression. You see that it's dependent on V over C, which is your classic telltale sign of a relativistic effect. What supposedly surprised Einstein, what he said was, I'm surprised this ends up being 1/2. If you go to the non-relativistic limit, this number here becomes 1 over 1 plus 1, which is 1/2. And it didn't go to 0, right? But it kind of does. I mean, you have the V over C here, so it does kind of go to 0. But the fact that this goes to 1/2 is what caught everybody by surprise for some reason. I don't know why this wasn't noticed right away. I mean, Thomas figured this out in 1927. Apparently, they spent a few years wondering where this missing 1/2 was in the theory that to match with the experimental data. It took a lot to get here, I guess. But this is a bit surprising because it was just an unexpected, purely kinematical effect, right? That's what they keep saying. This is a kinematical effect. There's no forces involved here, right? There's no torques. I guess that's what confused everybody, is there was no reason to expect a torque to change the orientation of the reference frame. But it's not, it's just a kinematical effect that doesn't have a torque. And this is still debated, right? There are still papers about this expression. There are papers criticizing this expression, saying this isn't right, or this is correct, but for the wrong reasons. I saw a paper that made that claim, that this is actually two different effects that combine together to give you this, but explaining it the way we did is a bit hand-wavy. And I'm no expert on all of that stuff, but you can, with what you know now, you can dig into it if you're interested. Okay, so much for Thomas Precession and a lot of our review of special relativity. Next, we will go on to, I think, the topic of electromagnetic fields in a covariant form.